Dude, you can see Stitch in the bottom. Bro. Just wants so much attention. Look at that. Hey, time to be serious. Guys, I just want to thank everybody who's present here for coming and watching my presentation. Um okay, so this presentation is about the discovery and characterization of Divarasib, a potent covalent inhibitor of Kras G12C. This presentation is by me, of course, Goob Gob. Here's an image of Divarasib. Bada bada ba. Cool. So, if we're doing a drug, we kind of need to know what the drug's targeting. The Kras is a gene in DNA that encodes for the Kras protein. It's a small GTPase protein. You don't need to know what that is. Just need to know that it takes GTP. You don't need to know, but I'll tell you. It puts GDP in it. Um, oh. So Kras has an on-off switch in the cell signaling. So when GTP is in, it's on. When GDP is in it, it's off. That's all you need to know, okay? GTP on, GDP off. And then when it's on, it relays cell signaling. It relays multiple pathways. Boom, 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 boom. That's the sound. That's actually the sound effect it makes when it signals. Boom, 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 boom. Can you tell it's late? Can you tell? It relays growth cell factors from the cell to various pathways. So if it's on, boom, hey, I'm a cell. I'm gonna replicate that this is on. Boom, Kras G12C mutation. Oh my god, mutation. Oh my god. Trying to get like I take a mental image of this. Alright, cool. So really there's a single amino acid mutation. This is a something mutation, point mutation, I don't remember. This glycine, no. No. Guanine, the guanine is being changed into why am I blanking? Guanine turns into, oh my god. I'm blanking. I don't even know my four nucleotides. I should I should drop out, damn. So really this is glycine becoming into cysteine. This mutation is found in 13% of non-cell cell lung cancer. Um, and really what this mutation does is that GTP hydrolysis, so when GTP comes out, that's not happening when this mutation's there. So really, hey, this is bad. Let's drug it. Oh, psych. GTP affinity is really low, which means like it binds really bad to GTP, but there's just so much GDP in it, in the cell, that it just kind of counteracts that. So if GDP affinity is so low, it's going to be hard to get a drug to have good affinity. Also, this protein surface is kind of smooth, which means that there's just very low allosteric sites. So really, this pathway, if you follow my camera, like you got a ligand up here, and it attaches to this, boom, boom. And then it tells this Kras to go from inactive to active when this gef, whatever, puts GDP in. Oh my god, I'm active now. Oh, I guess I'll do stuff because I'm active. Boom, goes down here, turns on this, turns on this, turns on this. Oh my god, oh my god. Oh my god, oh my god. And then it's gonna go to the proliferation differentiation, which is just gonna tell the cell to just, mitosis, man. And then really, like after a while, this is just gonna go crazy. Like this is just gonna go insane. Like like some like after a while there's just gonna be too many. Just too many. It's just this is a model I'm making to showcase what happens when the Kras G12C mutate. Oh my god, it gets like a little trippy. This is a model I'm making when the G12C mutation occurs. Um, this is what happens when cancer. This is what cancer actually looks like in the cell, in the body. So, yeah. So this is a model I just made to demonstrate what cancer it. Can you pay attention? This is a model I made to demonstrate how cancer looks. Um, yeah, so this is really bad for you when this happens in your body. Um, so this is like bad. So really, we want to make a drug that gets like rid of it. Oh my god, I'm a drug. Oh my god. Oh my god. This is what happens when you take a drug compound. Can you tell I'm tired? I'm not tired. Yeah, so really you take a drug. Oh my god. The, oh, not that one. Really, the count's just we're taking back control from the tumors. Wow, this was a really a bad mistake. This was a really bad idea. I shouldn't have done this. Okay. Bro. Okay. Why'd I do that? It's not even funny. Was it? Comment down below if that was funny. So really, this protein, after a while, they just gave up. They were like upset. They're like, "Oh my god, we can't do anything." It's like, let's do something. Ostrom et al. And his team actually discovered this allosteric pocket adjacent to the cysteine 12. Oh my god! So really, this is just a pocket. It's an allosteric pocket. It's really nice. At least we can get a drug in this pocket. It's really shallow, but something's better than nothing. His team used fragment-based screening. Oh, they targeted the cysteine, and this pocket's really only active in the switch 2. No, the GDP inactive state. Um, so they were like, oh my god, we could use the cysteine 12 mutation as a covalent anchor for irreversible inhibition. Oh my god. So really, because of that, only cysteine 12 is present in the mutant. You're not gonna have like really that much non-selective activity issues, whatever. So this is irreversible. This is a mechanism I made. That's why it's not credited because I made it. Yo, shout out me. So really the sulfur from the cysteine, it's gonna go attack this Michael donor. Boom, 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 boom. Push arrows, push arrows. Oh my god. Shout out to the people that understand this. Really, and it's just gonna make this covalent bond. This is called irreversible inhibition because it takes a while for this covalent bond to go away compared to just like van der Waals or hydrophobic interactions or uh whatever other interactions. Not polar whatever. I don't know. So really, so because of this, uh we were able people were able to make drugs that targeted this. Really, with all these drugs, pay attention. Oh my god, Michael Donut, Michael Donut, Michael Donut. All these use an acrylamide warhead, which is like really cool pattern to see. These guys just all copy each other. And then even though they all do patents, they all just copy each other. But so really, so Torasib and Adagrasib is the two that are prevalent right now. But they're really bad and not they're not bad. They could be better. Okay, so really, this team, their scaffold was this quinazoline core visualized in red down here, and then they put the acrylamide that's visualized in blue. So whatever. Scaffold in red, this acrylamide blue. They know from other drugs that this position right here, oh my god, you can't see my mouse. This position right here, it reaches over to cysteine 12, and it just points this acrylamide, this mycodona up top here to the cysteine 12. That's what we want. That's what we want. Okay, SAR. I really like SAR, but no one's gonna get this, so it's fine. Um, they tried stuff, bada. All you really know is that this bottom one's the best. This bottom one's the best because this number's low, this number's high, this number's low, this number's low, this number's low. I've okay. You want low, high, low, low. Here's SAR. Oh my god, I'm covering the SAR. I'm covering what R group. Ugh, why did nobody tell me? Oh wait, I'm filming a video. So really, our group goes here. They just tried substituents. See what's good, see what's not. Okay. SAR2, other R groups, they just tried what's going on. Really, all you need to know is that this one's the best on the bottom. Because numbers low, this number's low, this number's high, this number's low, this number's low. Oh my god! Is that the fastest SAR table readout ever? Hey guys, this number's low, this number's high, that's good. Really this bottom one is now the Divarasib that that we're talking about right now. So really they really focused on taking advantage of these empty spaces and these back pockets. You can see here in compound 4, and the difference between compound 4 and Divarasib, like right here there's an empty space that they added a group of substituent to take advantage of. Methyl right here. There's a methyl that got added right here also. They're just taking advantage of empty space. Let's do it. Let's go. This is the cysteine. This is the covalent bond that's formed, visualized in green in this photo. Cool. How does Divarasib act against these other G12C inhibitors that we hate so much? Because they're not Divarasib. Divarasib is just way better in assays. That's all you need to know. Okay, what is this graph saying? I totally forgot. Give me a sec. I get like it's just that saying is like, oh, Divarasib's good. Yeah. Um, what is this graph saying? Oh, it's just like so. Left one, you add Divarasib. Oh my God, tumor gets smaller. My God, the tumor gets smaller. That's what we want. Goob gob. Yeah, I know. That's good. That's why I'm presenting on this. This is the what did I call it? Sensitive tissue model. The tumor size went down. In the non-resistant tissue model, it stayed the same. So that's better. Hooray, hooray. Here's some other graphs. Divarasib, lower potency. Divarasib, better. It has good selectivity. Blah, blah, blah. I don't care. I don't care. References, boom. Okay. Q&A. Oh, don't want to spoil that slide. Q&A. Comment down below if you have any questions. Oh no, I should ask this question first. Okay. Why does Divarasib only work on Kras when it's bound to GDP? GDP and not GTP. Let me know in the comments below why. Let me give you some time to think. Comment down below if you got an answer. If you get the right answer, I'll say something. I'll give you a comment. I'll respond to your comment if you get the answer. Thanks for watching my presentation. I appreciate it. Make sure to subscribe for more awesome chemistry presentations coming in the future. Make sure to subscribe for more awesome video ideas. Dude, I'm so tired. I can't even like do the video. Okay. Currently we're at 78 subscribers, so make sure to get that number up! 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 Get that number up!